Have you ever considered that the universe might just be a hologram? Or that we could live inside a black hole? In this video, we'll dive into the universe's most mind-bending and unexplained mysteries, from the enigmatic dark matter to the perplexing theory of parallel universes. Prepare to question the very fabric of reality as we explore these astonishing scientific theories and discoveries. Stay with us until the end to uncover the astonishing theory that could completely change our understanding of existence. The multiverse theory posits that our universe is just one of many that exists simultaneously in a vast multiverse. Imagine countless universes, each with its own unique physical laws, constants, and forms of matter and energy. This theory challenges our fundamental understanding of reality itself. Scientists have found potential hints supporting this idea in anomalies within the cosmic microwave background radiation and the strange behaviors observed in quantum mechanics. For instance, peculiar patterns in the cosmic microwave background suggest that our universe has interacted with others, leaving behind detectable traces. A renowned physicist, Max Tegmark, has categorized the multiverse into 4 fascinating levels. Level 1 describes regions beyond our observable universe that share the same physical laws, but differ in initial conditions. Level 2 suggests the existence of universes with different physical constants, where the rules of physics as we know them might not apply. Level 3 takes this a step further, proposing that all possible outcomes of quantum events actually occur in separate parallel universes, a concept rooted in quantum mechanics. Finally, Level 4 introduces the idea of entirely different mathematical structures governing these universes, leading to realities that are completely alien to us. The concept of multiple worlds isn't new. Ancient philosophers like Anaximander and atomists such as Democritus first toyed with the idea of countless worlds existing simultaneously. Today, the debate continues among cosmologists. Can the multiverse be empirically tested, or is it destined to remain a compelling philosophical concept? The lack of empirical testability is the primary challenge facing the multiverse theory. Without direct evidence, some scientists argue that it remains speculative rather than scientifically validated. The simulation theory suggests that our reality is an artificial simulation, much like a highly advanced computer program. In this scenario, conscious beings within this simulation may or may not be aware of their artificial nature. Imagine a world where everything you see, feel, and experience is meticulously crafted by an advanced civilization with computational capabilities far beyond our own. Philosopher Nick Bostrom has been a prominent advocate for this theory. He presents a compelling argument, positing that it is possible to simulate consciousness. Advanced civilizations have the computational power to do so, so it's statistically likely that we're living in one of many such simulations. Bostrom's hypothesis is grounded in the idea that future civilizations would create numerous simulations of their ancestors, and thus, the chances of us being the original, based on reality, are exceedingly slim. Simulation theory is often confused with virtual reality, but there are significant differences. Virtual reality is an immersive experience created by technology within our known universe, where users know they interact with a simulated environment. In contrast, simulation theory posits that our entire existence, including all perceived realities and experiences, is a product of an overarching simulation indistinguishable from what we perceive as real. The philosophical implications of simulation theory are profound. If our reality is simulated, it challenges our understanding of existence, consciousness, and free will. Are our thoughts and actions pre-programmed? What is the nature of the entities running the simulation, and why have they created it? These questions touch on the very essence of what it means to be human. Bostrom's idea has sparked significant debate, with figures like Elon Musk and other scientists contributing to the discourse. White hole theory. Unlike black holes which pull everything in, including light, white holes theoretically expel matter and energy and do not allow anything to enter. They are considered the time-reversed counterparts of black holes, presenting a fascinating and challenging concept in astrophysics. White holes differ from black holes in several critical ways. While black holes are regions of space where gravity is so intense that nothing, not even light, can escape, white holes are thought to do the opposite. They expel matter and energy, not allowing anything to penetrate their boundary. If a black hole is a cosmic vacuum cleaner, a white hole would be like a cosmic fountain, constantly spewing out matter. The existence of white holes would have profound implications on our understanding of space-time. They suggest a reversal in the flow of time within these regions, which could offer new insights into the fundamental nature of the universe. If white holes exist, they might provide answers to questions about what happens to information and matter that falls into black holes. Some theorists propose that white holes could be connected to black holes through wormholes, forming a bridge linking different parts of the universe or even other universes. Current theories supporting the existence of white holes primarily come from solutions to Einstein's field equations in the theory of general relativity. These solutions imply that if black holes exist, white holes could also exist as their time-reversed counterparts. However, the concept remains highly speculative and controversial. There is no direct observational evidence for white holes, and many physicists argue that they are merely mathematical artifacts without physical reality. Critics point out that the conditions required for a white hole to exist are highly unstable and unlikely to be found in nature. White holes remain a speculative concept proposed by solutions to Einstein's field equations. Some theories suggest they could be linked to black holes via wormholes, creating an intriguing yet unproven bridge in the universe. Superfluid spacetime theory. This theory proposes that spacetime behaves like a superfluid, a state of matter with zero viscosity. This could explain certain quantum phenomena and the structure of the cosmos. Imagine the fabric of reality flowing without friction, seamlessly connecting all events and objects. A Bose-Einstein condensate is a state of matter formed at temperatures close to absolute zero, where atoms occupy the same quantum state, behaving as a single entity with zero viscosity. This concept relates to the superfluid spacetime theory, suggesting that spacetime could exhibit similar frictionless properties on a cosmic scale, potentially explaining the smoothness of gravitational fields in quantum interactions. If spacetime behaves like a superfluid, it could flow without resistance and form vortices under certain conditions, possibly seeding the formation of galaxies and large-scale structures. This behavior might bridge the gap between the smoothness of general relativity and the quantized nature of quantum mechanics. Experimental evidence could come from observing anomalies in cosmic microwave background radiation, gravitational waves, or particle behavior in high-energy physics experiments. For instance, unusual galaxy rotations or dark matter distributions might hint at superfluid spacetime. Laboratory experiments replicating Bose-Einstein condensates also offer insights. The idea is based on the properties of superfluids observed in labs. If spacetime acts similarly, it could revolutionize our understanding of gravity and quantum mechanics. Ekpyrotic universe theory. The ekpyrotic universe theory is a cosmological model suggesting that the universe undergoes a cyclical process of birth, cooling, and rebirth through the collision of hyperdimensional branes. This fascinating concept provides an alternate perspective on the origins and evolution of the cosmos. Unlike the Big Bang model, which begins with a singularity, a point of infinite density and temperature, the ekpyrotic theory explains the universe's origin through the collision of branes. Branes are multidimensional objects proposed by a string theory. In this model, our universe is one such brane, and its collision with another brane triggers a new cycle of expansion and cooling, avoiding the singularity problem by initiating each cycle with finite, manageable conditions. Branes play a crucial role in this theory. They are essentially higher dimensional membranes existing within a larger dimensional space. When these branes collide, the energy released during the collision sparks the formation of a new universe. This process repeats in an eternal cycle of contraction and expansion, providing a continuous creation narrative without the need for a singular starting point. The ekpyrotic theory offers several advantages over the traditional Big Bang model. It addresses the singularity problem by eliminating the need for an infinitely dense starting point. Additionally, it solves the horizon problem, the question of why different universe regions appear to have the same temperature, despite being causally disconnected, by proposing that the universe had a long cooling pre-collision phase, allowing for uniformity. Proposed as an alternative to the Big Bang, this theory provides a potential answer to what occurred before the Big Bang. It leverages concepts from string theory and aims to solve significant cosmological problems, offering a more comprehensive understanding of the universe's life cycle. Goldilocks planet theory. The Goldilocks planet theory refers to planets located within the habitable zone of their stars, where conditions might be just right to support life, similar to Earth. These planets are neither too hot nor too cold, but just right for liquid water to exist, a key ingredient for life as we know it. To be considered a Goldilocks planet, a planet must have several critical characteristics. Firstly, it must orbit within its star's habitable zone. where temperatures allow liquid water to persist on its surface. The planet should also have a stable atmosphere that can support life, an appropriate mass to maintain gravitational pull, and, ideally, geological activity to recycle nutrients and support a dynamic environment. These planets are crucial in the search for extraterrestrial life because they offer the most promising environments for life to develop. Finding a planet with conditions similar to Earth increases the likelihood of discovering life forms, whether microbial or more complex. The existence of such planets suggests that life could be more common in the universe than previously thought. Recent discoveries by space telescopes like Kepler and TESS have significantly expanded our knowledge of these potentially habitable worlds. Kepler in particular has identified thousands of exoplanets, many of which reside in their stars' habitable zones. Some of these planets are Earth-sized and show potential signs of having liquid water. These findings have ignited hopes of finding life beyond Earth and have propelled further missions to explore these distant worlds. The discovery of numerous exoplanets in habitable zones has expanded our understanding of potential life-supporting worlds. Missions like Kepler have identified many such planets, igniting hopes of finding life beyond Earth. Sterile neutrino theory. The sterile neutrino theory suggests the existence of a type of neutrino that does not interact via the standard weak force, making it a candidate for dark matter. Unlike ordinary neutrinos, which interact through weak nuclear forces, sterile neutrinos interact only through gravity, making them incredibly elusive and challenging to detect. Sterile neutrinos differ from ordinary neutrinos in that they do not engage in weak nuclear interactions, meaning they are sterile or inert and only influenced by gravity. This makes them an excellent candidate for dark matter, which does not emit, absorb, or reflect light and is detectable only through its gravitational effects. Sterile neutrinos might explain dark matter by providing the missing mass that influences the gravitational pull observed in galaxies and galaxy clusters. Since they do not interact with light, sterile neutrinos remain hidden from direct observation, fitting the profile of dark matter. Recent experiments, such as those conducted by the Liquid Scintillator Neutrino Detector, LSND, and Mini-Boon, have suggested the possible existence of sterile neutrinos through anomalies in the neutrino oscillation experiments. While intriguing, these hints still need to be conclusive and require further investigation. The existence of sterile neutrinos could solve several cosmological mysteries, including the nature of dark matter and the asymmetry between matter and antimatter in the universe. If you enjoyed this video, please give it a thumbs up and subscribe to our channel. If there's a topic you'd like us to explore, let us know in the comments below. Your suggestions could be featured in our next video.